I encourage you all to try. It's not so different from what we have done so far. So just give it a try and see. Maybe just some unique stuff here. Under the section .data, you see len, EQU, then the $sign, then MSG here. Okay, later in this class, you get to know what EQU is for. Let me give you a tip for constants, okay? It's for declaring constants. And ×9 is the only thing that changes here. Okay, that is a keyword that allows you to print out anything in multiple numbers, as you may state it. So ×9 means you're going to do that 9 times. The section .data, you have message, and then the defined byte is displaying 9 stars. And then what you see here, let's move on like this. Displaying 9 stars, it means that message is going to be used in somewhere in the code for syswrite. Okay, so you see message here, and then len equals, or the EQU constant MSG. This is to say that we want to always say the length of this message will be defined by the number of bytes we have defined already here. Okay, so unlike the last time when we worked on it, we were literally counting. We were counting how many bytes. You remember that? Okay, so you can use this line to sort of refer to the number of bytes in a particular defined byte, so that you just call this variable len somewhere else in the code, okay, in your syswrite. Do you guys follow? Okay, so that's literally what is there. And then as to the variable name here, ×9 is the only keyword here that is enabling us to do *9 times. Okay, this is where we ended the other time. So segment registers are specific areas in a program that contains data, code, and stack. Now I'll add a fourth one because I want to eventually talk about data segments, code segment, stack segment, and then there is another one called extra, okay? Extra segment. So in a 16-bit processor, that is the 8086 microprocessor architecture, we know that it is 16-bit wide, and then it has got data segment, code segment, and then stack segment. And then the last one is the extra segment. Okay, so you should take note of that. So by its name, extra, you know, we feel like it's just an addition to what is already existing. So usually in some books, you find that it say that there are 3 main segments, okay, in a register. There are 3 main segments or segment registers, which is the data segment, the code segment, and the stack segment. Okay, in other books, you also find it as 4, where they mention the extra. And in the end, also, as we move on in this slide, you see the introduction of the extra I'm talking about. So the code segment contains all the instructions to be executed. Okay, so one of the 16-bit code segment registers is the CS. So if you look at the nomenclature of the register and you see the CS, it tells you it is what? It is what? A code segment register. That's the idea you should get. So if you look at the cheat sheet of the registers, you can trace to identify. Usually, the reason why we may be teaching you from the level of 16-bit is that once you get to understand these registers in a 16-bit wide register or in a 16-bit wide processor, you can easily understand how the registers are in other processors, like in the 32-bit and other later ones like the 64-bit and so on. You understand? Because they sort of follow some line of nomenclature. Mostly the registers in the various processor architectures are the same, mostly, not all, mostly. Okay, so you would find that in the course we refer a lot to 16-bit, although 16-bit is, I mean, it's not necessary even now. Okay, who does 16-bit now? You know, but we kind of just refer to it because it's a way, or is that the starting point to get a further understanding into how the other registers in the processors are. Right. Then the next one is the data segment. That one, it contains the data and then constants, okay? Just like what we saw before I started the slides, how you use EQU to define a constant. So this segment of registers, or if you like, this segment of the registers in the processor will contain the data, constants, and other work areas. So the nomenclature for such registers is also DS. Okay, data segment. All right. So note that it also stores the starting address of the data segment, whereas the code segment stores the starting address of the what? Of the code segment. Okay. Right. The last one is the stack segment, and it contains data and return addresses of procedures. Okay, or if you like subroutines, like the gentleman asked us the other time. Okay, so that one also follows the nomenclature of SS. Okay, so please take note of that. And also it stores the starting address of the stack. Okay, so apart from the DS, CS, and SS registers, here we are talking about it in terms of 16 bits nomenclature. Okay, there are other extra segment registers. This is what I talked about initially. Okay, so in other books you see the classification as 4 segment registers, but here we're saying 3 main, and then we eventually mentioned that there is an extra segment. Okay, and that one goes by the nomenclature FS and GS, which provides additional segments for storing data. Okay, now the reason for this extra segment is because of the limitation of the number of bytes of memory that you can access within a processor, because there is a limitation, especially in the 8086-bit processors, with respect to how many bytes you can address at a time. Okay, that one is called 64K limitation. You can read about it later. Okay. All right. Okay, so in assembly, a program needs to access memory locations. Okay, maybe this is what I started talking about. Not only in assembly, in every other high-level programming language or object-oriented, whatever, every program needs to access memory locations. Okay, so with the around 1976 down to the 80s, the kind of processors that we had would only allow you to have access to that 65,350 bytes of data, as I was referring to. Okay. Yeah. Yeah, so all memory locations within a segment are relative to the starting address of the segment. The segment register stores the starting address of a segment. So that is to say, if you talk about code segment, it just stores the starting address of the what? Of the code what? Yeah, it's pretty simple. To get the exact location of data or instruction within a segment, what we do is that we use an offset value. Right. So to reference any memory location in a segment, the processor combines the segment address in the segment register with the offset value of the location. I'll repeat that again. To reference any memory location in a segment, what the processor does is that it combines the segment address in the segment register with the offset value in the location. So let me now come back and give you a fair overview of all these things that we've been talking about, and you get a beautiful idea, and then we continue. Okay. So in summary, I'm going to use a whiteboard to show you that. Have different kinds of processors. Please listen, pay attention. This is one of the important parts. If you want to be able to do non-trivial assembly language programming, you need to understand segments very well. And you need to understand registers very well. So you know which registers can be leveraged at this time or which ones cannot be used at this time. Okay, it's very, very important. So the first type of registers that we talked about is general registers. Yes or no? Okay, good. So we talked about it and mentioned data registers. Is that also? So data registers, we've learned that is part of the general registers, or in some books you find general purpose registers. Now, in the 16-bit, I'll give you the nomenclature. You should have it as AX, and then BX, CX, DX, SI, DI, and then BP, and then SB. All these registers are referred to as general purpose registers. So it's a set or a group of registers that we are talking about here. Now you can quickly identify this from the cheat sheet of the registers, right? So you know if it is in 32 bits, now this is 16 bits, but if it's in 32 bits, how does it move? Like you have E here, right? So you have EAX, EBX, and then you go on and on. But at some point, you realize that the nomenclature changes. Do you understand? So it doesn't strictly follow the XX pattern, right? So you have SI here, DI, BP, SB. Now we call these ones general purpose registers. Now, the reason you have to know that these are a set of general purpose registers is because we want to tell you that if you are programming in assembly and you want to do arithmetic computation or any kind of computation, then the class of processors you should look at using is this. This is the class of processors you should be using when you want to do computation of any sort, okay? Yes. So which ones here are data registers? Yes. Is what? Yes. Okay. AX, BX. Okay. And then C is a counter register. You see that? But they are all in there. They are all called general purpose registers. Do you guys follow? Okay. Now, why is it important to know that AX and BX are data registers? Anybody? So AX is a data register. We sometimes also call it an accumulator. Okay. You can do arithmetic operations in the AX. Okay. Usually you can let it be your destination. Okay, because usually in a line of a program in assembly, the source doesn't change after the step. What changes is the destination. So you can think of AX, whether RAX or EAX, if you want to use any register as an accumulator, then you should rather look at the AX family. Okay. Now, this is not to say that you cannot use other registers here as accumulators or as whatever. But then it is recommendable that AX registers are the most efficient if you want to think about accumulators or any arithmetic operation. Please, do you understand? Okay, you should get this basic strongly, I think. And then the next one I will talk about is the BX. The BS usually refers to as base. Now, what it does is that you use it to hold indirect addresses. Okay, now when we say indirect addresses, what do we mean? Right? Just like how the pointer registers work. The pointer registers are indirect. Is that not so? If you see a pointer register in an assembly program, there is no value that it is actually holding. It doesn't hold any value, but it is rather indirectly pointing you to a particular value. Is that okay? Yes, so the BX behave just like that. Okay, so that is it. The third thing that you also need to know is that the CS register, as we mentioned, is a counter register. Okay, so as the name implies, use it to count the number of iterations or the number of loops or the number of characters that can be stored in a particular register, okay? Or the number of characters in a string and whatever. So anytime you are thinking about counting, okay, counting, then it's the best register to use is a CX. Okay. Now, in a syscall, which register does the counting? Okay, syscall for, let's say, 32-bit or syscall for 64-bit. For write, let's just say so. Yes. Is what? Is what? In 32-bit is what? EDX. Okay, let's see. The next one is the DX. The DX register also is a data register. Okay, so AX, BX, CX, DX. Now, what it does is that it has two special purposes. It holds the overflow from certain arithmetic operations. Please note this. When we start division, you would get to understand what I mean. DX holds an overflow from a certain arithmetic operation. Okay. So for example, in division, you get to see that. Okay, and it holds input and output addresses when accessing data. All right. Now you have SI, and DI. They have special purposes as well. You may use them as pointers, okay? And then you can also use them to have your indirect memory addressing, okay? So just like we learned about pointers, typically that's what SI, DI does. Okay. Now what about SP, which is also a pointer? Yes or no? SP is also what? Pointer. Okay. And then what's the last one? BP, right? It's also a pointer. So you can see that within the general purpose registers, we have data registers, we have counters, and we have what? Pointers. Yes or no? Okay, and that's what we've been talking about all the time. Pointers are for indirect addressing. Are you guys here? Pointers are for what? Indirect addressing. And what are the registers that we use for pointing. BP, SP. Are you guys here? Okay. And then we are saying that counter registers is literally for counting. How many characters, what loop has happened, and so on. All right. Okay. And we know the nomenclature. And then we say we have also data registers. Data registers can be used for arithmetic operations. Okay. And some are meant to store an overflow, for example, the DX. Okay. And so on and so on. So you see the three classes of general purpose registers right here, and their nomenclatures. Okay, so this is necessary for us so that when we are writing an assembly program, we know which register to access at a time in a line. Do you understand? Okay. And then apart from knowing which register to access, when you are reading, literally reading an assembly program, you will then have some good understanding of why. Okay, you have a very good understanding of why some kinds of registers were used in the code. Are you guys following? Okay, good. So now the next set is what I call the segment registers, which we talked about today. But even before that, in our class, we mentioned control registers. Is that also? Okay, so the control registers, I said that in other books, you find the name as special purpose registers. Okay, now the registers that are used for this special purpose or control registers is IP. Okay, the 16 bits, that's the nomenclature. Okay. IP. And then the other one is flag registers. Okay, flags. These two, in the class, we said that these two kinds of registers combined to give you what we call the control registers. Is that also? Or in other words, the special purpose registers. So IP is an instruction pointer. IP is what? Okay, is an instruction pointer. And then we know about the flags, like the zero flag, overflow, trace, and all of that. All right? Carry flag and all of that. Okay. So I told you that you can read about it. The flags simply shows the state of the processor. That's all. Okay. So although the flag register in the 8086 is also 16-bit wide, it only can hold a value of one bit. Okay. Just like an electrical on and off. Okay. So it's either 0 or 1. So now, what changes the flags often is when we are doing a lot of conditionals and all that. Okay, conditional statements and all of that. When we are changing the program flow with certain levels of conditions, then you begin to realize that you set the flag, okay, and even sometimes in some arithmetic computation, you set the flag either to on or off. So that's one of the central things you should always remember. But there are then different kinds of flags, as you may find in your slides. Now, what is the third registers we know? That's the segment registers. Is that not so? Okay. So the segment registers is what we have looked at today, and we said that the set is made up of CS. What is CS? Code segment, right? Okay, code segment. And then the next one is what? DS. Okay, and then what is ES? Who can be smart with this? Extra segment, awesome. Okay, and then SS is what? The stack segment. So by their nomenclature, again, we can trace from the cheat sheet now to also identify all the segment registers. Please, do you understand? Hello. All right. So that is quite important for us. And we know what the code segment register does. Why? What does the code segment register do? Yes? Yes, bro? Yeah. Or it keeps or it holds the starting address, okay, of the registers used in the code segment. Let's move on, friends. So what we are saying again is that the segment register has got its own set of registers, like the CS, DS, ES, and SS. CS is code segment, DS is data segment, and so on. Okay, now I want you to think about it in this way. If you want to talk about segments, okay, first you can picture it like when we're doing our assembly program, we had to put it in segments. Is that also? And then we're not mixing up that thing. If we had .text, then we understood that that is where we keep all the instructions. Is that also? So we don't mix up by putting every execution instruction in another segment, right? Okay, so that's what we are thinking about. So think about it like blocks in the memory. Yeah, when we say memory, we're referring to the register, okay? So the segment register, think of it like blocks. That's what I was saying, like a two-dimensional space, okay? Like maybe like this. Okay, so, and then there are small blocks that way, okay? Small blocks like that, okay? So each block is a segment. Are you guys following? Each block is what? A segment, okay? It goes on and on like that, okay? So that kind of thing. And we are saying that there is y-axis and there is what? X-axis. It is a two-dimensional thing. And then I was mentioning that here is for offset value, okay? Because when you are plotting a graph, you need values for y and x, is that also? So the value here that will help you to locate a particular block here, okay, on the x-axis is an x, which is the offset value, which is needed, okay, in case you want to address or refer to a particular block in this two-dimensional space. And you also need the y value, which will be like, in this terms, if it's a code segment, then you're actually referring to the y value for the code, okay? So we are saying that the code segment actually refers to, or the code segment register, that's the CS, if you see that, refers to the starting address, okay, of the code segment. If we say of the code segment, here we are referring to of the segment where execution takes place. Are you guys following? Okay, so we know in the code segment what happens there? Execution. Okay, that is where execution takes place. All right. Same place, if you want to access a data segment register from this block, you still need an offset value to be able to locate that particular block, so to say, in your register. Okay. Right. So let's see, the last one. So the data segment register, which is the DS, it points to global variables for the program. Okay, and like I said, within the 8086 processor, you are limited to the bytes of data that you can access in a particular data segment, okay? And that is 65,536. But in advanced programming, if this limitation exists, then programmers cannot do any non-trivial application. So with the help of the extra segment, and then with advancement in Intel, you know, those who manufacture the processor chips, okay, with the advancement in their development patterns, now programmers are able to even access more than that. But with the extra segment, they were able to now access something like 1 megabyte. So there you see quickly the extra segment comes in. That enables you to modify other segment registers, okay? So code segment registers have their limitation, the same 64K limitation. In other words, you can't access more than 65,000, blah, 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 all right? Data segment has the same limitation, but with the help of the extra segment, you can modify the segment, either the code segment or whatever segment, to take more. So that's it. And then the stack segment. The stack is where you just keep the machine state information, okay? In whatever state the processor is, the stack is what keeps memory of it. And then it's in the stack that we deal with things like procedure, subroutine, returns, like we mentioned the other time. For references to subroutines, for references to procedures, then you need stack registers to do that, okay? But the special purpose registers like the instruction pointer and then the flags, you do not use them. You can't use them, okay? These are special purpose, or in other words, control registers. So in your assembly program, if you start using pointers like IP, instruction pointer, okay, in your assembly program, it means you are wrong. You can't use them. You can't use flags in your program. You guys get that? They are special purpose registers that they combine, okay, for the purposes of, number one, identifying what is the next execution point in your program. And this is useful to the processor, okay, not to be accessed by the program. Okay, so dear friends, that's what we've been talking about the registers. Okay, so we run down from general to special purpose and then to segment registers so far. So I suppose that by this time, when you look at the register chart, you have a fair idea of what each one of them means. In register addressing mode, we say a register contains the operand. A register contains the operand. Okay. Now, as processing data between registers does not involve memory, it provides the fastest processing of data. Okay, so in other words, if you're doing register to register, it's faster than register to some variable and a certain variable to register. Do you understand? Okay. Now, immediate addressing. An immediate operand has a constant value or an expression. And when an instruction with two operands uses immediate addressing, the first operand may be a register or a memory location. Okay, memory location, in other words, more or less like an indirect addressing register. So now let's take an example. Byte value DB150. Here, a byte value is being defined as 150. But what is the byte value? It's just an expression, okay, or if you like, a variable. And then we are saying that the value 150 is going to be in this byte value. Do you guys get it? Okay, so that you can call byte value anywhere. This is the kind of addressing we are referring to. Okay, so an immediate operand has a constant value, which is like 150 here, or it has an expression that when an instruction with two operands uses an immediate addressing, the first operand may be a register or a kind of a memory location, or if you like, a variable. Okay, and then the second operand may be a constant. So that's what we call an immediate addressing. So if you look at the addresses, the instructions here, move AX 45H. 45H is a constant, okay? And this constant is being moved into a register AX. Are you guys following? Okay, so that's what we talk about when we say immediate addressing. So you have your constant on the other hand moving into a particular memory location or a particular register. So no need to go over this. But it's important to mention that the move instruction may have one of the following 5. You can either do move register to register, register to an immediate constant, memory to an immediate constant, register to a memory, and memory to register. Now notice this. What else can you not do with a move instruction? Anybody being smart here? You cannot do what? You can't do immediate to immediate, right? Okay. And what else? Immediate to what? You cannot do immediate to register, right? Okay, so you should notice this, what you can do and what you cannot do. Okay, my time is up.